So in this screencast, we are going to do the second part of gas laws, which is all things about the ideal gas law. And this involves all four of the properties of gases that can be variable. So pressure, volume, temperature, and moles of a gas. So the ideal gas law is the mathematical relationship between all of the variables that can be measured within gases. Pressure, volume, moles, and temperature. And it's PV equals nRT. Some people call it PIV-NERT, just because that's what it looks like. So in this equation, this is the mathematical relationship between the four variables. So if we have three of the four variables, then we can find the fourth. Now keep in mind, we've got pressure must be in ATM, volume must be in liters, moles, well, it must be in moles, and temperature must be in Kelvin. And the reason for those things is because of this constant, which is called R, or it's the ideal gas constant. And the ideal gas constant is a constant that gives you the mathematical relationship between the four variables. And the ideal gas constant is given in liters and ATMs and moles in Kelvin, which is why these units must be in ATM and liters and moles and Kelvin. So, if they're not, if your pressure's not in ATM, your volume's not in liters, your temperature's not in Kelvin, you need to make sure that you convert into those units so that you can use this R constant and you can do your ideal gas law questions correctly. So in this practice problem, we're going to be practicing with the ideal gas law. So let's remember the ideal gas law, PV equals nRT. And let's start with the things that we are given. So in the problem, they are telling us that we have a 4.75 liter container. Well, there's our volume. And they're saying in this container there are 67 grams of nitrogen gas, and it's at 37 degrees Celsius. So that's our temperature. And the question is, well, what's the pressure in the container? So we know two of the three things right now. We know the temperature, we know the volume, and we can potentially get the moles, and that's going to allow us to solve for pressure. But we have some issues right now. So let's start with what we know. The volume is equal to 4.75 liters. We know that we have 67 grams of nitrogen. Here's the problem. That needs to be in moles. So we're going to convert that into moles. There are 28.02 grams in a mole of nitrogen because this is a diatomic gas. And that's going to give us 2.39 moles of our nitrogen. And then our last one is temperature, and the temperature is 37 degrees Celsius. And the problem that is Celsius, so we need to convert it to Kelvin by adding 273, and that gives us a total of 310 Kelvin. So now everything's in the right units that we need, because the last thing that we need is R, and R is equal to 0.0821 liters ATM moles Kelvin. And that's why we need all of these things in these correct units. So we're going to calculate the pressure. So the pressure is going to equal the moles times R times T divided by V. All I did was algebra, move the volume over to this side. Now let's plug everything in. Pressure is equal to 2.39 moles times 0.0821 liters ATM moles Kelvin. That's the unit for R. Times 310 Kelvin. And we're going to divide all of that by our volume, which is 4.0 0.75 liters. Now, I want you to take a minute and look at this. So look what happens with our units. If you set this up correctly, you should get units that cancel out and be left with the unit of the variable you're trying to calculate. So here we go. So moles on the top, moles on the bottom, they cancel out. Kelvin on the top, Kelvin on the bottom, they cancel out. Liters, liters, and what are we left with? ATMs, which is the unit for pressure. So now we just take all of this and we plug it into our calculator, and we get pressure is equal to 12.8 and the unit is ATM. So sometimes we encounter a derivation of the ideal gas law, which involves another characteristic of the gases, and that would be density. So we have to go back to the beginning of chemistry when we first learned density, and remember density is equal to mass over volume. So we can use this equation to calculate the molar mass or the density of some gas. If we end up calculating molar mass, we're going to be able to identify the gas. So here's the equation. Molar mass is equal to dRT, D being density, okay, R being the gas constant, T being the temperature, over pressure. My PowerPoint has this out of line, but I'm just going to write it right here. So dRT over P. Sometimes we call that the molar mass kitty cat, and because cats put dirt over their pee, the molar mass kitty cat puts dirt over their pee. It's just a derivation of the ideal gas law where we take into account mass, volume from the density part, and we also have to remember that molar mass is the mass of a mole. So if we take into those two equations, we can figure out this derivation. So how are you going to use this derivation? This derivation is going to be all about giving density, temperature, and pressure and finding the molar mass, or being given the molar mass and the temperature and the pressure and finding the density. A lot of times it'll be finding the molar mass, and once you find the molar mass, then you can identify the gas. The last concept I want to talk about in this video is about something called standard temperature and pressure. Standard temperature and pressure, also abbreviated as STP. Now, this is a situation that scientists have used to help us do the ideal gas law a little bit faster and not having to do long, cumbersome calculations. So here's what they've said. Scientists have established that standard temperature is 0 degrees Celsius and standard pressure is 1 atm. If you have a gas that is at 0 degrees Celsius and 1 atm, then we don't have to worry about you putting those two factors into the ideal gas law. Because if you did, if you plugged in those two factors, so if you plugged in pressure and you took the volume and plugged it into PV equals nRT, if we were to rearrange this and plug in 1 mole right here, plug in 0 degrees Celsius or 273 Kelvin and 1 atm, if you were to rearrange this, you would find that calculates out to a volume of 22.4 liters. So to make our life easier, we just use this number. So it says, we say if a gas is at STP, then we don't really have to completely use the ideal gas law. We can just use this relationship. 1 mole of any gas is going to have a volume of 22.4 liters. So it doesn't matter what the gas is, if it's oxygen, hydrogen, nitrogen, whatever, carbon dioxide, water vapor, it's always going to have a volume of 22.4 liters if you have 1 mole at 0 degrees Celsius, 1 atm. So how might we use this situation? It's actually going to make your lives a whole lot faster for stoichiometry if the reaction is taking place at STP. So here's an example. What is the volume of 3.5 moles of carbon dioxide? And we're assuming that, or we would say it's at STP. So if we are at STP, then we can use the relationship 1 mole is equal to 22.4 liters. So we're just going to use that as a conversion factor. So we're going to start with 3.5 moles of carbon dioxide. And for every 1 mole of carbon dioxide, that takes up 22.4 liters of space. And then we just do the calculation with our calculator, and we say 3.5 times 22.4, and that gives us a volume of 78.4 liters. And this is going to be like a shortcut to help you. So if the gas is at STP, we can just use this mathematically derived relationship. 1 mole has a volume of 22.4 liters.